So they're important sets. Now let's do definitions. Definitions. All right. So this is going to be our definition of even numbers. So for all n and z, n is even if and only if there exists a k and z such that n equals 2k. And by the way, this is exactly how all definitions are, right? Like we have the thing we want, n is even, the thing we want to define with a biconditional, and then we say how it's defined. Hope that makes sense. And all this is saying is that evens are multiples of 2. Are multiples of 2. Right? Because this is saying for every natural number, or sorry, for every integer n is even if and only if for some other integer k and z, n equals 2 times that k. So if n equals 2 times an integer, that means, well, n's a multiple of 2. So it's just saying n being even means n is a multiple of 2. Make sense? Now odd numbers are interesting. For all n and z, n is odd. So this is the definition of odd, if and only if there exists a k and z such that n equals 2k plus 1. So this just says odds are evens plus 1, basically, are off from evens by 1. Which should make sense based on our intuition how these things work. Any questions on this? Okay. Now we're going to define what it means for one number to divide another number. This is going to be the divide symbol. So for all a and z, and for all b and z, we say a divides, no, not like that. We say a divides b like that with a vertical bar. So this means the way you'd say it is a divides b. And what do you guys think? How would you define this notion of a divides b? Like, for example, we say 3 divides 6. Why does 3 divide 6?
Because it goes into 6 twice. Is that right?
Yeah, because it goes into 6. Because it goes into 6 a whole number amount of times, or an integer number of times, right? So 3 divides 6 since there exists an integer 2 such that 6 equals 2 times 3, right? Meaning 3 goes into 6 an integer number of times. And that's exactly how we're going to make this definition. A divides B, we say that A divides B if there exists some integer k such that B equals AK. Actually, I write it KA. I don't know why. Doesn't matter. So all this is saying is that A divides B if we can find an integer such that B equals A times K. A times that integer, right? Meaning, by the way, so all this says is that A divides B if B is a multiple of A. Right? Any questions on that? Good. That's important. That will come up. Now we can divide prime. This was cool. For all P and Z, we say that P is prime if and only if P is greater than 1 and, this is going to look weird, P is greater than 1 and for all Q Q divides P implies Q equals 1 or Q equals P. All right. This is the really mathy way to write this. Can someone translate this for me? What is this actually saying here?
P is prime if it's only divisible by itself in 1.
Exactly. P is prime if it's bigger than 1 and it's divisible by itself in 1 only, right? This part right here is saying that if Q is a divisor of P, it must be itself or 1, meaning all divisors of Q are itself or 1. So this means P is prime if greater than 1 and its only divisors are itself and 1. And these, are, by the way, are called trivial divisors. Just because duh, obviously, any number divides itself. 1 divides any number. So it's trivial. All right. Last definition. Then we can actually go with the proof. So composite. That just means the opposite of prime. And so we could say for all N and Z, N is composite if and only if we have the opposite of N is prime, right? N's not prime. But N not being prime, a way we can write that, actually let's keep it like this. But what's this mean? This means for all N and Z, N composite, if and only if, like if we kind of negate this definition of prime here, what we get is that P is less than or equal to 1, or there exists a Q, these should be in the integers, by the way. There exists a Q in the integers such that Q divides P and Q does not equal 1 and Q does not equal P. And this right here is literally just the negation of this, right? Like we flipped the P greater, like the opposite of P greater than 1 is P less than or equal to 1. The and flips to the or by De Morgan's law, right? And then once we negate this, the for all attention there exists. And then the opposite of if hypothesis, then conclusion is hypothesis and not conclusion, right? So we're saying there does exist some integer that divides P that's not 1 and it's not itself. So there does exist some non-trivial divisor. All this means is that P is composite if P is less than or equal to 1, or P has a non-trivial divisor. All right.
Professor, quick question.
Yeah.
Trivial divisor as in like very specific, right?
A trivial divisor, which up here I mean to mean itself or 1. So the trivial divisors. So trivial divisor of like 5, for example, are 1 and 5. Right. So the trivial divisors. Oh, you guys can see that. The trivial divisors of anything are just itself and 1. The trivial divisors of 100 are 1 and 100. Trivial divisors of 314 are 1 and 314. Makes sense? They're really obvious ones. And so P is composite if P is less than or equal to 1, or P is a single non-obvious divisor. All right. Any questions?